correctly. Okay, I think it's time to start. So, any question from this time? If not, then yeah, let's get started. So, this time we start talking about the postulates of quantum mechanics, and we have a simplified version here, where we say that the simplified version says that the quantum state is a vector in a unit vector in a complex vector space. This will represent the state of a quantum system. And the quantum state can be changed by unitary matrices. Okay, and you need to be unitary because you want the length of your state. The length of your vector to stay as one. And then at the end of computation, we can do the computational basis measurement. And when you do computational basis measurement, you will collapse your quantum state into computational basis states. So those I. Okay. And with probability alpha I squares, and your state will turn into I, and it will stay in I until you do other things. And when you have multiple systems, H1, H2 to Hn, etc., and then the state of the total system is a tensor product of all the subsystems. Okay, so H1 tensor H2 tensor Hn. And the tensor product is what we talked about in the previous chapter, and is a huge space where the dimension of the product of the space is the product of all the dimensions. Okay, so those are 1, 2, 3, 4 simple postulates, and then we start to talk a lot about the measurement, because measurement is really what's really weird about. Depending on what you view, but measurement is one of the parts that's very of quantum mechanics that's very different from classical mechanics. Okay. And so we start to talk about 4 different measurements. I guess 3 different measurements, but there are actually 4 of them that people will talk about when they say quantum measurement. Okay. So first one, this is 0th one, is the computational basis measurement we just talked about. And it is when you measure a state, then you just look at its amplitude, those coefficients A0, A1, A2 on computational basis. And then you will, when you measure in computational basis, the state will get turned into a computational basis state, and with the probability equal to the absolute value of amplitude squared. And then there is a measurement against the orthogonal basis. And there is a measuring a Hermitian operator, and there is a generalized measurement. Okay, and as we said, a measurement against orthogonal basis is really similar to a measurement against computational basis. Just instead of the computational basis element here, you have whatever orthogonal basis you have here, and the probability of getting ice outcome is the amplitude on the ice computational basis element. Ice basis element here, and the post measurement state will be your orthogonal basis element here. Okay, and so we have an example. So obviously, computational basis is an orthogonal basis. So you can think about your computational basis measurement just as a special case of orthogonal basis measurement. And then you can change your basis to do measurement, and you see that you can measure instead of the 0, 1 basis that will measure with probability A squared and B squared, you can have the measurement in plus minus basis. Then you will get the outcome state as plus with probability A plus B squared over 2, and outcome minus with probability A minus B squared over 2. Okay. And you see that instead of measuring in different orthogonal basis, you can do a changeable basis first, and then just do computational basis measurement. So in terms of computational power, those 2 are the same. Okay? And then we have this very physical thing that's measurement by a Hermitian operator. And so this is kind of what the physicists think about measurement. You measure some physical quantity. Okay? And anyway, so in quantum mechanics, people think every physical quantity is related to a Hermitian matrix A. And remember, a Hermitian matrix can be unitarily diagonalizable into with real eigenvalues. So A can be written as the summation I, lambda I, and projected onto all the eigenvector Vi. Okay, where Vi's are the eigenvectors associated with the eigenvalue lambda I. Okay. And so when we say we measure by the Hermitian operator A, we are basically saying it's basically just measuring in orthonormal basis. Okay, it's very similar to measuring orthonormal basis because we know if A is Hermitian, then also Vi will form an orthonormal basis. Okay. So yeah, it's very similar to we just measuring this orthonormal basis. That's this orthonormal basis. That's just the eigenvectors of A. Okay, but there are two differences. Okay, when you say you measure a Hermitian operator. Okay, so first is just a syntactic difference. That is the outcome. Before we say like just you get the ith outcome and you kind of know the outcome is I, and now we just label outcome differently. We say when we measure some Vi, then we say the outcome is this eigenvalue lambda I, because this will relate to some physical quantity. So maybe this lambda I is your position, so it's 2, then your major outcome is your particle is at position 2, etc. Okay, so you just label the outcome as lambda I. And the second difference is that you can have degeneracy. So degeneracy is when several eigenvalues of A are having the same number. Okay, so there can be some lambda I and lambda J that are equal to each other. And in that case, then the eigenvector correspond to the Vi and Vj that are not unique. And instead of measuring to the orthonormal basis element, we are measuring to these projectors. Okay, so we define those projectors onto the eigenspace of A with same eigenvalues. Okay, so there might be several independent eigenvectors that have the same eigenvalue, and then this thing will have more than one dimension. Okay, so we have this Pn that's project the projector onto the whole space that all have eigenvalue m. Okay. And instead of writing A as a summation of projection onto eigenvectors, we write A as this summation of projection onto eigenspaces with different eigenvalues. Yeah. Okay. And we'll use this Pn to determine our post-measurement state. Okay. This is really small. But anyway, when we measure quantum state size with observable, then basically what happens is the state will get turned into Pn psi with probability. So with probability Pn psi amplitude length squared, and then the post measurement state is Pn psi normalized. Okay, and yeah. And then there is also one extra thing, that is the expected value of the measurement can be easily calculated by this formula. That's this psi bra A psi kit. So A sandwiched by psi. Okay, and here we have an example that this sigma x we really like is actually an operator, a measure operator that can be measured, and you can think about measure x with this plus state. Measuring x on this 0 state, and you will get probably 1/2, you get plus 1 outcome, probably 1/2, you get minus 1 outcome, and the expected value is 0. And then we have an example of measuring an operator that has degeneracy. So you see that observable A here is 2, 1, 1, so this eigenvalue 1 has degeneracy 2, and so for this eigenvalue 1, you want to calculate the projector onto its eigenspace, which is this projector 0, 1, 1. Okay. And for probability of getting one outcome is the length of your projection onto this 1, 1 space. and for the outcome 2, there is a projection onto the first space, etc. Okay, and we say that the degeneracy will happen a lot because there are composite systems. Okay, and finally we talk about generalized measurement. Okay, generalized measurement it's very generalized, so it's a little hard to see the intuition behind it. But basically, you can do a quantum measurement with whatever set of matrices, as long as those set of matrices satisfy this complete listing relationship. So I should say completely. So this is usually called completely this kind of relationship, kind of called complete this relationship. Okay, and so whatever set of matrices that satisfy this thing, and obviously with the correct dimension so that they can act on site, it define the measurement. Okay, and just similar to the Hermitian measurement result. So the hint here, I guess let's see this first. So you will get some outcome I with some probability, and so outcome I happen with probability is length of mi psi squared. Okay, and then and you can check that this probability is equal to 1 as probability should, and then the final state will collapse into mi psi normalized. Okay, and so once again the hint here is you calculate mi psi. Then the probability of this happening is the length square of this thing, and then the final state is this thing normalized. Okay, so when you get all as outcome, you basically get this thing, and so with some probability, and then you need to normalize to this thing. Okay, normalize the state. Okay, and also just a bit of terminology. So those MIs are called measurement operators. Okay. And so we have a few examples of how to view previous measurement schemes as I guess a few examples of what this generalized measurement actually generalizes the previous measurement scheme we talked about. So for example, we can think about orthogonal basis measurement. So we have some orthogonal basis, the state of VI. And then how we write it as a generalized measurement is, so now we need to find those MI, and MI will just be projected onto those VI. So this is a VI cat, VI bra. Okay. And then you can check things. So so first you can check what's your MI psi. So MI psi will be about MI psi will be VI cat, VI bra times psi, and this is just number, so you know the post measurement state is just VI. Okay, and then from here you also kind of see that and you can see zero thing, and also you can check that mi dagger mi equal to this VI projector times VI projector, and it respect to VI projector, so equal to mi. Okay. Yeah. So this thing is equal to mi dagger mi equal to mi equal to this VI projector. Okay. And then you can check it out. The probability is this psi mi psi, and that's just the amplitude square on VI, as we said in the orthogonal basis measurement. Okay, so that's a small review of what we've done this time. Any questions so far? If not, then let's continue on our generalized measurement. Okay. And so we have an example. So psi is in 1 qubit, so psi is on A0 plus B1, and we say we measure in this 0, 1 basis. And then okay, so now we want to write things in more complicated notation. Then we have 2m, so we have m0 equal to 0 projector, and m1 to equal to this 1 projector. Okay, and yeah, and the probability of getting zero outcome is this zero projector on side and squared. And once again, you do the calculation, you will equal to a squared, and the probability 1 will be this n1 projector 18 on side and squared, and that will be this b squared. Okay. And so something interesting happened here, and we come back to the last thing we want to talk about in measurement. That's the projective measurement. Okay, and that is we see that I guess back in the very first slide of measurement schemes, we say the first two or first three schemes are projective. And what do we mean by projective? Means that the mi in the measurement operator mi for them are projectors. Okay, and that will make things a little easier to write, because for projector, okay, and when we say projector, we actually mean Hermitian projector. Okay, so let's say Hermitian here. Hermitian. Okay, and so the first measurement scheme, or just as the example we see here, the measurement operator are projectors, and because projectors is defined as pi squared equal to pi, and we say we also assume mi is Hermitian, so and we also assume mi dagger equal to mi. Okay, so mi dagger equal to mi and mi square equal to mi, and so we have that. So we have mi dagger. So what we have is that mi dagger mi equal to mi. Okay, so yeah, so this is actually what happened. So mi dagger mi will equal to mi. So things are a little easier to write. So the completeness relationship you can just return as summation of those pi equal to identity, and then outcome I will happen with probability pi on side squared. Well, this is the same, but the middle one is a little easier. It's this side pi side, and yeah, you can once again check that the summation pi equal to 1. And the outcome I happen with this probability. And when outcome I happen, then the state collects into, well, still pi side, pi side, and normalized. Okay, and yeah, but anyway, so these are projective measurement. Projective measurement just means that your measurement operator are Hermitian projectors, so that mi dagger mi equal to mi. Okay, and yeah, then finally we can go to our postulate of quantum mechanics. Okay, and so this is a detailed version. So postulate 1, we say that associated with any isolated physical system is the complex vector space with inner product. Okay, and that's called Hilbert space. And yeah, later, so this is actually kind of important that it is isolated here. Okay, so right now we are talking about isolated physical system. But anyway, so we have a Hilbert space, that's the state space of the system. Okay, so any physical system, we think we want to describe all its property, then we are writing a complex vector in this Hilbert space. Okay, and then here is a bit of physics thing. So the dimension of the vector space depends on the physical system. So you can think about if your system is more complicated, then it can hold more information, then the dimension of the space should be larger. Okay, so like maybe just an elementary particle, you have like maybe 2 or 3 dimension, and you have a lot of particle, then you have a lot of dimension. And also in physics, sometimes the dimension is infinite, but that's something that we don't take care of here. We assume our dimension is finite. Okay, in this class. And yeah, just as we said, then the system is completely described by its state vector, which is a unit vector in this Hilbert space or state space. Okay. And yeah, and this vector is called quantum state. Okay. So here we have several terminology that we'll use interchangeably throughout the course. So we will say, well, most of the time we'll just say quantum state of your system. And obviously you can also say state vector and or like a state of the system. Okay, and as we see, usually the quantum state, this vector will denote it as a kate vector. So it's a column vector, so like this kate. And here is a little bit of a postulate that people also think is true, but also say that is, we also think any unit vector in the Hilbert space is a valid quantum state. Okay, so it's like sufficient and necessary. So if you are, so every valid quantum state is a unit convex vector, unit vector, and any unit vector is a valid quantum state. Okay, so so you describe a quantum system as a complex unit vector in a Hilbert space, just as like a simple example. Okay, and just like our simple version of the postulate. Excuse me. And then postulate of quantum mechanics 2, we say that the evolution of a closed quantum system. Okay, so once again here, this thing only happen for closed, and so if you read the later part of the book, we actually talk about how open quantum system is described. But for now, let's talk about closed isolated system. Okay, so evolution of a closed quantum system is described by unitary transformation. Okay, so unitary matrix, and that means that if you have a state psi at some t1, and you will get changed to some state psi prime. Excuse me. So little typo here, and so you start with some state psi at t1, and you change to some state psi prime at t2. And then psi prime is equal to u of psi. Okay. And so it's written as like psi, usually write like psi equal to psi prime equal to u of psi. Okay. And this u need to be a unitary matrix because you want this to be a unit vector and this also to be a unit vector. Okay. And then here we can digress a little bit, and we talk about this postulate 2' that we don't actually use in English class, but it's be nice to know. That's a famous Schrödinger equation that you will learn in physics class. Okay, and so Schrödinger equation is a differential equation that tells you how a state evolves through every time step. So here you have this continuous time here. And so you write this differential equation, so IH bar d psi dt equal to h of psi. And so this t is time, and h bar is some physical constant. And h is Hamiltonian, so it's a Hermitian matrix. Okay, basically you have a Hermitian matrix that so Hamiltonian is it's also a quantity. So excuse me. So Hamiltonian usually represent the total energy of your system, and energy is some physical quantity you can measure. So actually you can measure the Hamiltonian, and as we say, each measurement operator is represented by a Hermitian matrix. So this Hamiltonian is mathematically it's a Hermitian matrix that in principle can be measured, and when you measure it, it will tell you the total energy of the system. Okay. So if you want to see how your system evolves through every time step, you just calculate, I guess, then you know it's Hamiltonian. Your system will specify its Hamiltonian, and you have some starting state, and you evolve your state by this differential equation, then you will see your system at a different time step. Okay. And so I guess the difference between postulate 2 and the postulate 2' is here we actually have continuous time. So here time is something just evolve continuously, which we think is normal, but we are in computer science, so actually in postulate 2 we kind of think time is discrete here. Okay, so here we are just thinking about discrete time step. Time is discrete as in our computer. Okay. So time is discrete in our class. So we just think about things happening in class cycle, just like in your CPU. So we just think things will happen step by step. So you have some discrete time step. I guess this is a little ambiguous. So let's not write this. Time is let's say time is discrete in this class. Okay. And yeah, so we just think things happen time step by time step, and for the between each time step is you apply a unitary to your system. Okay. Yeah, that's like a simplified view of our computers. Okay. And yeah, so that's the postulate 2. And postulate 3 we talk a lot about. So postulate 3 is the measurement of quantum mechanics, and here we take the most general form, so we have a generalized measurement. So quantum measurement is described by this collection of mi, which are just matrices, and I call these matrices called measurement operators. And the matrices must satisfy the relationship, that's summation over I, mi dagger mi equal to identity matrix. Okay, and I correspond to different measurement outcome. Okay. And just a review again. So when you measure a state against the set of measurement operators mi, and so one and only one outcome will happen, and the outcome I will happen with probability pi equal to this norm of mi psi squared. Here we have a little typo. Sorry, norm of mi psi squared, and you can check that the probability sum to 1. Okay, you can check the probability sum to 1. And when outcome I happen, then you will learn the outcome I happens. So you will learn this label I. And also the really weird thing about quantum mechanics is that when outcome I happen, then the system collapses. So system basically collapses into this mi psi state. Okay. And so it becomes mi psi normalized. Okay, so that's quantum measurement. And finally, we have this postulate 4. Okay, so postulate 4 is often omitted. Often, a lot of times omitted, but omitted when talking about postulate of quantum mechanics. But I think it's really something you need to written in postulate. Okay. So it says that you have a composite physical system. So here, once again, I guess the important part is the composite physical system. Okay. So if you have several quantum systems putting together, interacting with each other quantum mechanically, then then we want to describe the system together as kind of the combination of subsystems. Okay. And what happens is you need to use this tensor product structure that we talked about to describe them. Okay. So the state space of the composite system is the tensor product of the Hilbert space. Okay. Just like we talked about previously. Okay. So that's those H1 tensor H2 tensor H3 . Okay. And so the Hilbert space is a tensor product of each other, and if the system was prepared, so if each subsystem is prepared in some quantum state psi, then the joint system is also in the tensor product of states. So this is psi 1 tensor psi 2 tensor psi. Okay, and here I also put on 2 more postulate that. Okay, so this is about, so the postulate 4 should we actually have a section for each of the previous postulate. Okay, so this is about the states, and about the unitary you have well, kind of similar thing. So if you do a unitary U on some subsystem A, then what you are doing is so on joint system. So remember this U is this U is unitary on a small Hilbert space. Then you want a unitary on the total Hilbert space. Then it's you just put identity on all the register. Okay. So so this is the eighth. Okay. So you are doing U on each slot of your Hilbert space, and you are doing identity on all other system. Okay. So yeah, U on subsystem A is I tensor U, then so it is U and a tensor. You can think about you do a measurement on subsystem A, and then the measurement operator on Hilbert space HA will get turned into this measurement operator on the total Hilbert space, and that is similar to the unitary one. You just tensor a whole bunch of identity on all other systems. Okay, so I, tensor mi, and tensor I. Okay, in composite system, and yeah, we will talk about the composite system maybe next week. Yeah, the composite system is I think it is a lot of where weird quantum computation thing happen. It is because, as we say, it is I guess one of the way people say quantum computer can have exponential speed up is because the dimension of the composite system grows exponentially with the number of subsystems. Okay, so this is kind of a critical part of why quantum computation works. Okay. Okay. Yeah. So it's kind of ignored, but kind of over ignored, but it is an important part of quantum mechanics. Okay, and so if there is no question, so I guess we'll come back to the details about composite system later, and let's kind of go back to the weirdness of quantum measurement again. Okay, and I want to talk about this idea of unknown quantum state. Okay. And yeah, so this is really some idea that you don't have classically. Okay, so classically, if you have a system, then if you don't know about it, then you can measure it and you will learn about it, right? So like every people here, you have your height and weight, and if you don't know your height, and then you go stand next to a meter and then you learn your height. And then you don't even know your weight, then you stand on a scale, you will learn your weight. Okay, so you have a physical system classically, then in theory you can learn all its property. You just measure your system with various devices and the matrix. Like you can even learn your body mass. You can I guess you can even learn the percentage of fat in your body, etc. Right? And but quantumly that's not something true, right? That's because quantum measurement. Okay, so we keep talking about quantum measurement will collapse in a changing state, and but I just want to stress again that the collapsing quantum state is a really weird thing. That's because if you don't know, okay, oh sorry, a typo again. Okay, so this is something kind of paradoxical. So if you don't know what a quantum state is, then you will never know what it is. So you basically need to know a little bit thing about quantum state to learn what it is. Okay. But anyway, let's go back to you never know what it is part. Okay. So if you don't know what a quantum state is, then you will never really learn what it is, because you can measure it once in some way, and that measurement will very likely change your state. And then change the state, and you never learn the original value of your quantum state. Okay, and so for example, you have some quantum state, simplest quantum state, a quantum state in in a qubit. So this is a two-dimensional quantum state, psi equal to A0 plus B1. So you don't know what A and B is, and you try to learn this A and B, and so maybe you measure in computational basis. And what happens is you measure the state and it will just turn into 0 and 1. And with the probability A squared and B squared. Okay? So if you see a 0, then you think maybe A is a bit larger, and you think it's 1, and you think maybe B is a bit larger, because if B is larger, you are more likely to get 1, A is larger, more likely to get 0. But that's it. So you measure it once, and they get it turned into 0 and 1, and then you no longer get any information about A or B. Okay, so yeah, you measure it once, and it just collapses into 0 or 1, and So information about A and B is gone forever, and so you will never really learn about A and B. Okay. So that's a really weird thing about quantum state is if you don't know it, and then it's very hard to learn it. Okay. And this is called unknown quantum state. It means quantum state in some dimension that you just don't know about its coefficients. Oh, go ahead.
We just measured a lot of times to know it's A squared or B.
No. So we're going to talk about this next slide. Okay. Okay. So order. Okay. So if you measure, it once, you turn into 0 and 1, and okay. So it kind of goes like this. Okay. So let's start with the simplest thing you can do. So you measure it once, you turn into either 0 or 1 with some probability, right? And then if you keep measuring the 0 with computational basis measurement, what happens is it's 0, and you just say, well, it's 0, and it's 0 in computational basis. So measure again, you just keep going until 0, 0, 0, 0. And if you measure this 1 with computational basis measurement, again, you just keep telling you 1, 1, 1, 1, 1. So only when you measure first time, you get some information about A and B. Okay. And I guess then a reasonable question you might ask is, will you measure this quantum state once and it disappear? Then that's annoying. How about I copy it, and then we can have multiple copies to measure it. Okay, so each copy I can measure it and to get 0 and 1, and then we hit with this no cloning theorem. Okay, and the intuition about the no cloning theorem is that you cannot copy an unknown quantum state. Okay, so we have actually very short mathematical proof here. Okay. And yeah, so if you have arbitrary unknown quantum state, then there's nothing you cannot really copy it. And the formal statement is that you cannot have a unitary that do the copy. Okay, so let's look into the mathematics about copying. Okay, so you have some arbitrary quantum state side here, and you want to copy it. So copy it, you need to write it into other space. So suppose your Hilbert space, you have two registers, so you have this side register, another register that initializes to some standard thing 0. And so you have a copying unitary, copy your side to 0. So you apply this U on your side and the empty space, and it becomes 2 copy of side. Okay. So I want to see whether we can have a copying unitary that work for all sides. And we see that you cannot. So suppose so if you want this to happen, then you need to happen for 2 different states, right? So suppose you have 2 different states, psi and phi, and then you have that u psi 0 become 2 copy of psi, and u phi 0 become 2 copy of phi. Okay, and then u is unitary, and so we can. Oh, sorry, I'm jumping ahead a little bit. Okay, so we have this equation and this equation, and we kind of do inner product between those 2 equations. So left hand side inner product with left hand side, right hand side inner product with right hand side, and then we have this psi 0 u dagger times u psi 0 equal to this psi inner product with phi phi. Okay, and now back to using that u is unitary. Then we see that this u dagger u is identity, and then we remember. So this u just become identity and cancel out each other. So now we just have a tensor product of state inner product with tensor product of states. And then we remember tensor product is just you calculate each slot separately. Okay. So the left hand side become psi phi inner product times 0 0 inner product equal to 1. Okay. And the right hand side is psi phi inner product times psi phi inner product. Okay. So we see the psi phi inner product equal to psi phi inner product squared, and that means that this thing is 1 or 0. Okay, and so you see that even if you only want to copy 2 different states, so you want this only work for 2 different states, you need to have a restriction that this psi equal to phi. Either psi equal to phi means inner product equal to 1, or psi and phi are orthogonal. Okay. And in particular, that means that if you want to copy psi in the file that for example, inner plot equal to 1/2. Okay, so for example, if you have psi equal to 0 and I guess for example, if you want to copy 0 and the plus at the same time, at the same time, impossible. Okay. Yeah, so there is no cloning theorem says that you cannot copy arbitrary unknown quantum state, because basically actually we prove something a lot stronger. We say that copying any two states that are now orthogonal to each other is impossible. Okay, and okay, so there is no cloning theorem, and let's talk a little positive. That's back to what if we just have a lot of copy. Okay, so we have this quantum state tomography. So we have just unknown quantum state, and we are guaranteed to have many unidentical copies. So suppose this is produced by some experiment, and you can keep doing the experiment you can repeat the experiment to produce many copies that are just we think they are identical. Okay, so we have those side, and then we can learn this side by doing measurement on it. And but the caveat is you need a lot of copy. Okay, but anyway, so for example, you can back to our example of psi equal to a0 plus b1. Then we can learn a squared and b squared by doing computational basis measurement. So kind of like this. So we have a lot of copy of psi, and you measure it, and each measurement will tell you it's a 0 or 1. Okay, and so then you can count how many 0 you get here and how many 1 you get here. So the fraction will tell you estimate of this a squared and the b squared. Okay, and so that's from here you will learn a norm of a and b. And if you want to totally learn this state, then you also need to learn the phase of a and b. And I'm not going to do this here, but it can be done. Okay, so you can learn, but obviously you cannot do this by just computational basis measurement. So you need to do measurement in other bases, and you will learn the phase and b. And yeah, then you can learn this quantum state. And the more copy you use here, the more precise you get on your estimate of a and b. Okay, and there are actually very strong theoretical results. So people study this problem in a lot of detail. So in general, you want to learn unknown quantum state side to some fixed precision, where precision is to be defined much later over the class. Okay. And you need about theta d copies. So you need about this order d copies of psi, and d is the dimension of a Hilbert space. And because you know that from our composite postulate, we know that from our composite postulate, we learned that the dimension of a Hilbert space is exponential in number of subsystems. So this d is usually going to be exponential in the size of your physical system. And so to do a quantum state tomography is actually very expensive, even if you are given identical copies. So you just need a lot of copies to do them. Okay. And yeah, so that's the most brute force way to learn unknown quantum states. Okay, and we have 5 more minutes, but yeah, I guess let's keep going. Okay, so this is a hard thing to do, so quantum state tomography, and now let's back to a little bit of an easier case. So so let's talk about another problem. So I guess there are a lot of problems you can ask about in the unknown quantum state, and one of the problem is distinguishing quantum state. Okay, and yeah, so this problem is that say your psi is promised to be So the question is like this. So your unknown quantum state is promised to be either one of the two states, either psi 1 or psi 2. Let's say psi 1 or psi 2. And those two values are known, okay? And determine which. Okay, so you are given one copy of your unknown quantum state, and it's either this is psi 1 state or this is psi 2 state. And you know what is psi 1, you know what is psi 2, and you want to determine which one is given to you. Okay, and classically, once again, it's easy because you just learn this state and you see it's either 1 or 2 or it's neither of them. Okay, and in quantum case, sometimes this can be done. So if the psi 1 and psi 2 are orthogonal to each other, then they can be perfectly distinguished because you can extend the psi 1 and psi 2 to orthogonal basis and do the orthogonal basis measurement on this side. Okay, and so for example, this K0 and K1 can be perfectly distinguished because you can do the measurement 0, 0, this measurement, this computational basis measurement represented by projection on 0 and projection on 1. Okay, so if your state is 0, then your measurement result will be 0. If your state is 1, your measurement result will be 1. Okay, and similarly, this plus state and minus state can be distinguished by this plus minus measurement. Okay, and but you can prove that, you can prove that non-orthogonal states, so if a pair of states that are non-orthogonal, then they cannot be perfectly distinguished. Okay, and yeah, for example, so we have a non-orthogonal state, 0 and a plus. Okay, and so this is not quite a proof, but just an attempt to distinguish them by some measurement. Okay, so you have the 0 state and a plus, so you have a state. So basically you have a state psi, that's so you have a state psi that is either equal to either 0 state or plus state, and you want to know which is given to you. And so you can try to measure it in this minus, plus, and minus state. Okay, and then you need to consider two cases. So when you are given this 0 state and the 0 measured in plus and minus basis, then you will get plus state with probability 1/2 and minus state with probability 1/2. And if you are given a plus state, and this is a nice part. So nice part because plus state is orthogonal in this plus minus basis. So plus state will turn to the plus state with 100% probability. Okay. And so here we see that we don't have perfectly distinguished because sometimes you learn something. Okay, sometimes you learn something but you don't get perfectly distinguished. So you see that when you see outcome minus, okay, so you measure in plus minus, and so what happens is you will see outcome either minus or plus, right? So you see outcome minus, then it's good, because you know outcome minus can only come from you are given is 0 state. Okay, so you see outcome minus, you know your state was 0, but but if you have outcome being plus, then you don't really know which state you were given, because you might have a plus state to begin with, or this plus state might come from your 0 state got collapsed into a plus state. Okay, so this tells us that this plus minus measurement doesn't distinguish 0 and the plus state perfectly. Okay, and yeah, I think it's time for a break. So any question? Otherwise, let's take a break, 10-minute break. Okay, yeah, let's take a 10-minute break and continue this next class.怎样？
从那个横向变斜向这样的时候， 是不是要取公式
对，我们的定义基本上这样，就是转过去的时候要寻公了，就是一做 dagger，
存量的 tensor product 就是乘法嘛。
对啊，存量 tensor product 就是乘法，对，对。怎么？
这门课有小考吗？还是只有期中跟期末？
期中跟期末而已。对。
作业大概有几次？
作业大概还有12次。对啊，应该有13次、14次的作业这样子。对。
对，每个礼拜都。
对啊，每个礼拜都有作业。
所以就是今天结束之后又有。
对，会又有作业。
那个作业的解答会公布吗？
会公布，会公布。对。
有
很多作业。
那么多次作业只有占30分，有出这么多吗？
就是这样。让大家努力的练习。
老师打的。对吧？
什么东西？
这是什么？这是你打的，是老师打的。
这个是这是其中。应该是我打的，但我忘记为什么要打这个了。
这是你以前打的。
应该是我很久以前打的。
好，那。
我忘记我想要把题目变难还是怎样。感觉已经蛮难了。
我觉得数字已经没有到很好算。
对啊，应该比我变更难了。
好，那可以
看起来是，对啊，你可以把它取掉。
好。这个在做完碰。
我看一下，我们应该教得完吧？
可以啊。
这看起来都教了，对啊，应该就不用动吧？
那就先这样子。
你看一下有没有下一份的需要出来？好像也没有吧？
没有，应该是没有，因为下一份好像就是要。
那你可以改数字吧？就是那个 harder 的部分可以改数字，重新凑一下。
凑矩阵的数字。
但是2的部分，我在想，有点想，不知道能不能让你弄出来。我们能够弄个 composite 的，可是我们也没有讲 composite 就是。不是 composite 的 measurement 啊，就是有两个。就是有2个 subsystem， 然后我们也用一个 subsystem 的情况的。
你在 tensor 里面 i 什么之类的？
对啊。
i tensor 里面。
对啊，就有 tensor z 之类的。i tensor z 啊，某个 state 啊，某个 2-qubit state 这样子。
然后算它的几率这样。
对啊。主要是 post measurement state 吧 ，post measurement state 会比较奇怪。对啊 ，i tensor z 啊 ，post measurement 2-qubit state， 然后它的 post measurement state 这样。
算到了后面，会算到后
面。理论上还是做出来嘛，因为我讲 composite system 的 postulate。可以让我们试试看。
好，我再想一下好了。
对。就 i tensor z 啊，你可以就直接把 build state 丢上去嘛，比较简单，00加1的那个。
好。
对的，2根号分之00加1。对啊。
科吗？是那个它是量子态，然后这个我们观测它就会跑几率性产生不同的东西。
对啊。
那个量子态它是个有实体吗？还是怎么样？
有实体吗？什么意思？有实体吧？
它
就是量子系统它的状态啊。例如说，就 quantum computer 里面就有很多量子态嘛，就是它可能会是有很多实作方法，例如说它可能是电子的自旋方向啊，然后有时候会是超导的震荡的，那个比较奇怪，超导电路的震荡的状态啊，然后或者是光子偏振的方向啊，这算是实体吧？还是你要问非常哲学性的问题？量子状态你不能
就是装出来的东西都是几率性的，这样吗？
对，就是你看它会改变啦，我们是这样想的，它会有一个几率性的改变这样子。
看它就是两侧，
有可能两侧对啊，你去量测它的话，它可能会几率性的改变，对啊。那这个会几率性改变的东西到底是不是真的这个哲学的问题？有没有实体？对啊。
考试会考证明题吗？
考试会考证明题吗？好像比较少，但不能说没有。过去没有。对。说不定有，好像比较少吧。好像有。好像有吗？不太记得，好像有。比较简单的。好像有。对啊，所以好像是有证明题的。
所以还是有证明题。
对啊。
那作业的解答会公布吗？
对啊，作业解答会公布。
什么时候公布？
看助教什么时候打完，应该蛮快的。
明天我打完。
对啊，应该都还蛮快的。Hello. Okay, let's get back to our distinguishing quantum state. Okay, so as a small reminder, distinguishing quantum state is this quadrant that we are asked to do. So we have some state side, unknown quantum state side that's promised to be either one of the two states. It's either some state side 1 or state side 2. And you know the distribution of side 1 and side 2. And you want to know whether you are given whether the state is actually side 1 or actually side 2. Okay? And we know that if the side 1 and side 2 are orthogonal to each other, then you can perfectly done this question, this task. So you can just do a orthogonal basis measurement that has psi 1 and psi 2 as two of its vectors, two of its basis vectors, and then you will learn whether psi is psi 1 or psi 2. Okay. And but if the psi 1 and psi 2 are not orthogonal to each other, then they cannot actually be perfectly distinguished. For example, you have the 0 and the plus, and they cannot be perfectly distinguished. For example, so we just try one of the way to distinguish them. So we try to measure in plus minus spaces, and we see that 0 will have a probability 1/2 to become plus state or minus state, and the plus state will stay plus state. So we have some partial distinguishment here. So we see that if we see a minus outcome, we know the state we're given must be 0. But if we see plus outcome, then we don't really know it comes from 0 or plus. Okay. And we so this is just one way, but we want to say this really cannot be distinguished, perfectly distinguished. So we have a small proof here. Okay, so we prove that non-orthogonal state cannot be, I guess, perfectly distinguished. Okay, so perfectly distinguished. Okay, so what do we mean perfectly distinguished? We mean that we have perfect. Okay, perfectly distinguished. So we mean that we have some measurement that so so we have our psi 1 and psi 2 we want to distinguish. Okay, so we have an unknown state that's either psi 1 or psi 2, and perfectly distinguished means that we have some measurement m1 and m2. And so we'll do M1 and M2 on either psi 1 or psi 2. And when it's psi 1, the outcome should be M1. And when it's psi 2, so the outcome should be M2. Okay, so that means this M1 psi 1 norm square should be 1. And M2 psi 2 norm square should be 1. Okay, and yeah. And that also means that so when you measure N1 and 2 on psi 1, 100% probability you get N1. That also means there is a 0% probability you get N2. Okay, so N2 psi 1 equal to 0. And similarly, when you measure N1 and 2 on psi 2, you should have a 0% probability to get this one outcome. So N1 psi 2 square should be 0. Okay, and yeah, so this is what should happen. And now I can start to do some derivation. So we have that while psi 1 and psi 2 are not orthogonal, means that psi 1 and product psi 2 not equal to 0. And we write the psi 2 as a linear combination of its a component on psi 1 and its component that's orthogonal to psi 1. Okay, so we write psi 2 as a psi 1 plus b times some component that's orthogonal to psi 1. Okay, and crucially we use that since they are not orthogonal, then this a is not 0 and b is less than 1. Okay. 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 And so yeah, so because this psi 1 and psi 2 inner product is not 0, so a is not 0, and so b is less than 1. Okay, so we know psi 2 has some component. So the component of psi 2 that's orthogonal to psi 1 must be less than 1. That's just, well, not orthogonal. Okay, and then let's do some math. Okay, so we have well n2 psi 2. So we write n2 psi 2 as this decomposition. So psi 2 as a psi 1 plus b psi 1 perpendicular. Okay, so n2 psi 2 is a n2 psi 1 plus b n2 psi 1 perpendicular. Okay, and then finally we can use our condition given here. So we know n2 psi 1 is 0. So n2 psi 1 is is the probability of basically the probability of sorry, the norm of n2 psi 1 is 0 because that relates to the probability of a major psi 1 get the two outcome. So this is 0, so this is just b and 2 psi 1. Okay, And now let's take the known square of these the two sides of this equation. Okay, so so inner product of this thing with itself. So it's psi 2 and 2 dagger and 2 psi 2, and as we know, so this known square of n2 psi 2 is should equal to 1. And the other side is known square of b, and then is psi 1 perp times psi 1 perp sandwich in n2 dagger n2. Okay, and psi 1 perp sandwich and yeah, excuse me. So psi 1 perp sandwich and 2 dagger and 2 should be less than psi 1 perp sandwich and 2 dagger and 2 plus and 1 dagger and 1, because it is a positive operator. So you sandwich anything on it is positive. Okay, and then this is just identity, and so we see that this side is b squared. Okay, and but this is a contradiction, because we know from here, so so here is actually a little wrong. So I guess we didn't say. So the norm of b is less than 1. Okay, this is norm of b. Yeah. So basically what we do here is we recognize that this thing is less than 1, because it's on normalized vector, sandwiching something that's less than identity matrix. Okay, so this part is less than 1, and we also know b squared is less than 1. So you have two things that's less than 1 multiplied together that equal to 1, and that's impossible. Okay, and in terms of more detailed equation, we have this 1 equal to b squared, and but b squared is less than 1, and that's a contradiction. Okay, so 1 less than 1 is a contradiction. So you see that it's impossible to have n1 and n2 perfectly distinguishing your non-orthogonal psi 1 and psi 2. Okay, question? Yeah, so it's a bit of mathematics, but anyway, the intuition here is here. Now, orthogonal state cannot be perfectly distinguished. Okay, and then let's switch gears. So we still want to talk about measurement, but let's switch gear a little bit, and let's talk about block sphere and Pauli matrices. Okay, and so what's a block sphere is a very nice way to visualize a qubit, and qubit is I guess I should not say a two-dimensional quantum state. We should say a two-dimensional quantum space. Okay, space. Okay. So when we say a qubit is just a state with in a quantum state in 2 dimensions. Quantum space of 2 dimensions. Okay, and so block sphere is a very nice way to visualize it, and it's also related to Pauli matrices. Okay, which are also 2-dimensional matrices. Okay. So let's start with quantum state in 2 dimensions. So psi equal to A0 plus B1. And so we want to write it in this way. Okay. So we write this A and B as e to the I gamma. So we know that A and B can always write as this e to the I gamma cosine theta over 2, and B as e to the I phi sine theta over 2. Okay. And this is because I guess a little bit of derivation here. This is because we know that a squared plus b squared equal to 1. Excuse me. So this thing comes from a squared plus b squared equal to 1, and that means the norm of a is like cosine something. So and norm of b is like sine something. Okay, and so we just have cosine something as cosine theta over 2, and sine something as sine theta over 2, and that's only talking about norm of a and b, and they are phase on a and b. And so we just say the phase on A equal to this e to I gamma, and the phase on B equal to this e to the I gamma, e to the I phi. Okay, so A equal to some phase times the cosine of some theta, and B equal to some different phase, so B has a phase gamma plus phi, and the sine other thing. Okay, so that's the derivation of this equation. Okay, and actually, as we'll see later, so this e to the gamma, I gamma is called a global phase and doesn't matter, and it can be ignored. So in general, our state side can be written as cosine theta over 2 0 plus e to the I phi sine theta over 2. Okay, with well, theta from 0 to pi and phi from 0 to 2 pi. And so you can, from here, you can think of this. So you have this theta from 0 to pi and phi from 0 to 2 pi. Theta from 0 to pi and phi from 0 to 2 pi, and you can draw it on as a spherical coordinate on a sphere. Okay, so the theta and phi let you draw a point on a sphere. Okay, so then this sphere is called a block sphere. So you can always map a 2-qubit state to a point on a sphere. So this is a spherical coordinate. So you have a theta equal to this angle theta here, and a phi equal to this angle phi here. So we have a coordinate x and y and z, and whatever state a0 plus b1, you write it as cosine theta over 2 0 plus I e to I phi sine theta over 2 1, and then theta and phi are here, and you can find your state on this sphere. Okay, so this is a mapping from side to sphere. Okay, and obviously you see these mappings two ways, and so every state you can map to something on sphere, and anything on sphere you can also map to a state, like here. Okay, so you have a one-to-one correspondence between a state and a sphere, and you can check yourself that this theta from 0 to pi actually makes sense, because because you want this theta over 2 from 0 to pi over 2, so your amplitude from 0 to 1 and 1 to 0. Okay, and so that's the definition of block sphere is a way to, well, you map your 1-qubit state to points on your unit sphere. Okay, so that's nice. And but there are actually more structures, so we want to talk about polys. Okay, so actually, we have this x, y, z axis here on this sphere, and they actually correspond to our poly matrices sigma x and sigma y and sigma z. Okay, and what do we mean by that is that so it's actually already labeled here. So this x-axis, I guess it's actually related in multiple ways, okay? Because it has actually very deep physical background, okay? But anyway, so for now we can see that the plus state and the minus state, so this x-axis, the intersection of this x-axis on the sphere actually the two eigenvalues of your x operator. So this point will be the plus state, and this point will be a minus state. And similarly, the intersection of y-axis on the sphere will be the plus eigenstate of y and the minus eigenstate of y. And the intersection of the z-axis on the sphere will be the eigenstate of z. So this is plus 0 state and 1 state. And I guess let's try to do some calculation to see we are not wrong. Okay. And so for example, this plus state, it should have we have theta equal to pi over 2 and phi equal to 0. Then the state is So the state is cosine theta over 2, and so the state is cosine pi over 4 plus EI phi equal to 0. So EI phi doesn't happen, and sine theta over 2. And excuse me, cosine the state here. So the state at this plus point, the point that we claim to be plus, is theta equal to pi over 2 and phi equal to 0. So we have cosine pi over 4 0 plus sine pi over 4 0. Oh, sorry, sine pi over 4 1, and that's 1 over square root 2 of 0 plus 1 over square root 2 1. And yeah, so that's the plus state as we claim. Okay, and so yeah, so the xyz axis actually correspond to the polar matrix xyz, and that have several meaning. First one is the intersection here correspond to the plus 1 and minus 1 eigenstate of sigma y, sigma x, sigma y, and sigma z, and and also there is a unitary operation on the sphere. Okay, so actually you do a sigma x is a rotation about this axis. Okay, so that's a special case of a Mildred thing. Okay, so what do we mean is that actually every unitary operator on one qubit is a rotation on So every unitary operator on the sphere is you will rotate the sphere. Okay, so you will rotate every vector of the sphere. So for example, I guess sigma x is rotating what sigma x do is it will rotate the whole sphere by pi radian. Okay, well I guess it's ignoring global phase, so that's also something a little weird. But how you will rotate the mapping of the box sphere by pi radian. So for example, so if you do sigma x rotation, then because these plus state and minus state are just on the axis, so they don't get changed. Okay, but what about the zero state? Then excuse me. Yeah. And about the zero state, because you rotate everything by pi radian, so you rotate by half circle, so the pi will get, the zero will get rotated to 1, and the 1 state will get rotated to 0. Okay, and then you can think about maybe a state somewhere here, then you will get rotated to somewhere here. Okay, yeah, so everything will rotate in circle. So maybe a state somewhere here will get rotated to here, and the state here will get rotated to here, etc. Okay, and yeah, so that's a erase the ugly drawing. And yeah, so that's what we mean by unitary operator will rotate the sphere. Okay. And also the sigma x will rotate the plus y to minus y and the minus y to plus y. Okay, and then there's more. And then there's a little more we want to talk about the geometry of the black sphere. That's a little confusing. That is, the geometry of the black sphere is different from the geometry of the Hilbert space. So for example, you see that the K0 is mapped to this point here, and K1 is mapped to this point here. And so we think about the three-dimensional vector of this point is 0, 0, 1, and the three-dimensional vector of this point is 0, 0, minus 1. And well, these two vectors are not really orthogonal to each other, right? So they're actually on the same line. Okay, so 0 ket is mapped to this 0, 0, 1 vector, and 1 ket is mapped to this 0, 0, minus 1 vector, and well, they are on the same line of black sphere. but we also think the 0 ket and the 1 ket are orthogonal in our two-dimensional complex space. Okay, so here you see that when you map a 1-qubit state to a Bloch sphere, you are mapping a two-dimensional complex vector to a three-dimensional real vector, and that will distort your geometry a lot. So you see those two vectors that they are orthogonal in your two-dimensional Hilbert space. They're actually not orthogonal in your Bloch sphere, and that's just something you need to remember. So yeah, this is a little confusing, but you just remember that geometry on Bloch sphere is different from geometry in your Hilbert space. Okay, and yeah. And finally, well, there's something we want to say that we'll use later is that the Bloch sphere can be used to represent spin direction in real world. Okay, and so if your spin is in a two-dimensional space, then actually we think that if it's spinning in some xyz direction, then let's say that the state is in this Bloch sphere state. Okay. So maybe the spin is spinning in x direction, and then we will think is so this xyz direction can also be correspond to the xyz direction in real world 3D dimension, and spin in x direction will be in this plus state, and spin in this minus direction will be this minus state, and spin in z direction will be this plus 0 state, and spin if you are spinning in this minus z direction, then it's 1 state. Okay, and so that's about the spin. And finally, not finally, and let's go to talk a little bit more about Bloch sphere and Pauli. Okay, and actually, you can think about the direction. How to say? So direction on Bloch sphere or vector direction in 3 dimension can be written as some vector n x and y and z. Okay, and you can actually what do I say? I guess it's a little hard to see the connection here. Okay. So let's talk a little bit more about Pauli. Okay, so I guess the intuition is here. Okay, so we're thinking about Pauli x, Pauli y, and Pauli z correspond to the 3 axes of the Bloch sphere. Okay, and but you think about there are other direction on the sphere. Okay, and so does the other direction of the Bloch sphere correspond to other Pauli? So you have some. You can have some theta phi, so maybe this direction here, some theta phi direction, and that actually also corresponds to some Pauli. Okay, and that's this thing. So you have some theta y direction, then you can write down the directional vector corresponding to it. Sorry, some theta phi. So you have some theta phi point, spherical coordinate on your sphere, and you can write some direction vector in x, y, and z here. Okay, and then that direction actually have a corresponding Pauli. That's just you take the inner product between your direction vector with this funny vector of Paulis, and this thing is just defined by. So it's easier to see. It's just nx times your sigma x plus ny times your sigma y plus n. Oh, sorry, here is typo. Plus nz times your sigma z. Okay. Okay. So remember, so that's nx times your sigma x. So this nx times 1 1 plus ny times this minus I plus nz times your 1 minus 1. Okay. And you can return this down, and it's this matrix. So you write this back to your theta and the phi. Then it's this cosine theta minus cosine theta and e minus I phi sin theta, e I phi sin theta. And this matrix is a lot like Pauli matrices, because this operator is also it also has eigenvalue plus minus 1, so it has a lot of property of your Paulis. Okay, so for whatever x and y and z, that has the north square equal to 1, then you can write this nx sigma x plus ny sigma y plus nz sigma z, and it's like a poly in your x and y and z direction, and you will have eigenvalue plus minus 1, and so yeah, so let's think about you maybe draw it like here. Okay, so maybe you have some nx1 and y and z here, so nx and y and z. So you can have this poly in nx and y and z direction, and that means that the plus 1 eigenvector of this new poly will be on this point, and the minus 1 eigenvector of the poly will be here, and you can rotate, and when you apply this poly, will be rotated around this axis by radian pi. Okay. And example of this, well, I guess generalized poly is Hadamard matrix. So Hadamard matrix being 1 over square root 2, 1, 1, 1 minus 1 is 1 over square root 2 sigma x plus 1 over square root 2 sigma y. And so it's so Hadamard is actually, so let's erase. I guess I can be here. So Hadamard is actually in the middle of sigma x and sigma z. So the direction of Hadamard is like here. Okay, and yeah, and yeah. So coordinate is 1 over square root 2, 0, and 1 over square root 2, and have some theta and phi. And it also has eigenvalue plus and minus 1, and you have the eigenvectors you can solve for. Okay, any question so far about black sphere and poly? If not, and yeah, then let's go to a bit of physics. Okay, although yeah, go to a bit of physics. This is what I really like a physics experiment that kind of confirm why quantum mechanics exists. Okay, and this experiment will once again tell us a little bit about measurement. Okay. So this experiment is done like this. So so you have an oven here that heat up a whole bunch of silver atoms. Okay, and so silver atom, and being silver doesn't really matter. Only matter is that silver atom has a spin. Okay, silver atom has random spin direction, and so you have silver atoms here, and it heat up and shoot out as a beam. And so it has random spin direction because you have random atom shooting out. Okay, and you go through a non-uniform magnetic field in the z direction. And what happens is this non-uniform magnetic field will interact with spin in the z direction. Okay, so you think that okay, so non-uniform magnetic field interact with spin in z direction. That means that if you have more spin in z direction, then you will I guess it will deflect up, and you have spin in downward z direction, you spin down. Okay, and so you think that okay, so you think that if you are classical particles, and so if you have classical particles, and your spin is in random xyz direction, and it's kind of uniformly distributed, then you have a screen here, and the end result is you should have kind of a uniform distribution. Okay, so you expect kind of like this, expect kind of a uniform distribution like this. Because just you have a random spin direction, and you get deflected by a different amount, and you get a kind of uniform strip stretching in z direction. But what happens in experiment is that you only see 2 dots. Okay, so you see 2 isolated dots here, and so kind of like this. Okay, and so this is interpreted as being that the spin of the particle is actually in 1 qubit. Okay, So spin of a particle is 1 qubit, so it's either in this 0 state or 1 state. Okay? And if it's 0 state, and when you ask, when you go through this magnetic field, and you are basically asking whether your spin is up or down. And if it's up, then it's in this 0 state, and they go to this upper block. And if it's down, and it's in this 1 state, and they go down here. So when you go through this magnetic field, it's like you do a measurement of your sigma z, and then it's a basically like a computational basis measurement. And so if your state is 0, then so your state start with a0 plus b1, then with the a squared probability go up here, and with the b squared probability going down here. But everything just give you this either 0 outcome or this 1 outcome. Okay, so so this kind of go back to our block sphere. Okay, so you think about your initial state is in a random place in this block sphere. Its spin is pointing in random direction. But when you do this z direction measurement, then you only get this 0 outcome or 1 outcome. Okay, you don't get a uniform distribution of your spin. You only get it's either up or down, and so that's why you get these 2 blocks. And this is, I guess, the first experimental confirmation of quantum effect. Okay, and so this is what's been done experimentally. And but what's interesting is we can think about some sort of experiment. Okay, so what if we extend our Stenger experiment theoretically, and and we do it multiple times? Okay, and we can think about what happens if okay. So first we do our original Stenger experiment. So we shoot our spin of a silver atom. And you have a z directional magnetic field, and you will split the spin the atoms into 0 state and 1 state. Okay, so just like this, you split into 0 and 1. And so what if we just take all the 0 state string and make it go through an x directional magnetic field? Okay. And so this will be the same as well, you are measuring this 0 state against observable sigma x. Okay, okay. So remember sigma z is so remember sigma x is plus minus. Okay, so measuring sigma x is measuring in this plus minus basis. Okay, and so you measure the 0 state against plus minus. And you will see that once again with probability 1/2, you get the plus state, and with probability 1/2, you get a minus state. Okay, so basically you think about you to go through this x direction magnetic field again, and then your string should split in x direction. So if you put a string here, then you should see 2 blobs here, and one of them corresponds to the minus state, and another of them correspond to the plus x. Okay, and now let's get a little weird. Okay, so let's talk about something we kind of go through before. So if we go through a z field and we split our string into 0 and 1, and what if we take this 0, 1 and we go through another z field? Okay. And that's same as you measure the z against z, and well, as we said before, you measure the same thing twice, it should give you just the same result. Okay, so you measure 0 against z, and it should still give you 0. So this doesn't split your string. Okay. Okay, so you should have a 100% probability getting just this 0 result, which is also the plus 1 for your z operator. Okay, and yeah, so this is something to remember. So doing the same measurement again just give you the same outcome. Okay, so you do this measurement z, and you do measurement z again, it should give you the same outcome. Okay, and what's really weird is what if you measure in z direction and measure in x direction, z direction, and you take out this 0 string, and you measure x direction and take out this plus string. And what do you measure in z direction again? And what should be the outcome? Okay, and so here you might think, well, you are already pinking out the atoms that has spin in z direction here, right? So as we say here, if you have a z direction measure, you measure z direction and you measure z direction again, it should give you 0. Okay, and so here you measure z direction and you measure z direction again, so you should get outcome z, just outcome 0 here. But actually that's not what happened. What happened is this will spin again, because if you go through mathematics, here you are measuring this plus state against z, and you measure plus state. Sorry, you measure z on this plus state, and that should you measure sigma z on plus state, then you should actually get 1/2 probability of 0 outcome and 1/2 probability of 1 outcome. Okay, so even though your string was 0 because you already pick out a 0 component, and then after you do this x measurement and then you do z measurement again, then you see that once again it's split into 0 component, 1 component. So this z component string somehow after you do those measurements become 1 component, has some probability of become 1 component. Okay, and yeah, and this sounds a bit confusing, but this is what happened by the measurement rule. So remember, so this is consistent with the measurement rule we talked about in quantum mechanics. That is, when you do a measurement, then you just collect the state and then just forget what it was before. Okay, and so after you do a x measurement here, it collapses into the plus state and just totally forgot it was this 0 state. And so when you do this measurement of z direction again, the particle will once again be 1/2 on 0 and 1/2 on 1. And you can interpret this as being this 2-dimensional particle. This particle being 1 qubit is very stupid. You can only remember one answer. So you after you ask what's your direction what's your spin in x direction, and they say it's plus, then only remember that it's plus direction, and this plus in x direction, and you totally forgot its direction in z in z spin direction in the z direction. Okay, yeah. So you can interpret this as that this low-dimensional Hilbert space cannot hold too much information. So you only remember its spin direction in z or spin direction in x. Okay. And when you remember its spin direction in x, it totally forgot its spin direction in z. Any question? Yeah. And yeah, so once again, little finish. So comparison of those two, you see that what difference between this experiment and this experiment is that you do a measurement in the middle. So you see that just by doing a measurement in the middle can change the outcome of your quantum experiment a lot. Okay, and yeah. So yeah, so this HR measurement of x in the middle can change your quantum state. Yeah, so this is just reiterating that what we know, that's doing measurement will change your quantum state. Okay, in particular here we are doing measurement and select particular result. Okay, and I guess any questions so far on this Stern-Geller experiment? We have a little bit of time. I guess let's finish talking about phase. I don't want to. We don't have time to talk about POV, I think. Yeah, so let's talk about phase. Okay. So there is a little thing we want to prove, okay? And anyway, so phase is about complex number. So remember all the amplitudes in amplitudes in quantum computation are complex number, and the complex number has those fixed vector e to the I theta. Okay, and there are two different phases that either has a physical meaning or don't have physical meaning. Okay, so first thing is we can generally ignore what we call global phase vector. That is, say if your state psi has HR phase vector e to the I phi, and then this state is really equal to this state psi. And that's because whatever measurement you do on this vector is same as whatever measurement you do on this vector. I guess the measurement probability on this vector is same as the measurement probability on this vector. Because the measurement probability is written as, some mi, so some psi sandwiching your mi degree mi is same as your ei theta sandwiching your mi degree mi, because this ei theta will just cancel all this e to the minus I theta. So whatever measurement statistic you get on this e to the I theta side will be same as this psi. And yeah, so global phase doesn't give you any measurable difference between your states. Okay, so we ignore global phase. But there can be relative phase that will actually make a difference. So for example, you think about the two state, plus state and the minus state. So plus state is 0 plus 1 over square root 2, and the minus state is 0 minus 1 over square root 2. Okay, so you can see you have a different phase on your minus state, on your one state, case 1. Okay, so you have a plus here, and you have a minus here. Okay, okay, and yeah. Yeah, and so you see that these two states are just different by a phase on your Kt1. And we know those two states are totally different because, as we said today, they are orthogonal to each other and they are totally distinguishable to each other. And yeah, so you see that this relative phase between 0 and 1 give you totally different quantum state. Okay, and that's about phase. Any question so far? And I guess POVN, I guess we can finish this. And finally, we can talk about POVN, that is positive operator valued measure. Okay. And yeah, and this is really just a way to I guess be lazy about writing measurement. Okay, and that's supposedly we have some generalized measurement set of mi. Okay, and we perform then, as we said, when we do this measurement mi on the state side, the post measurement state will be like mi side, and the probability will be mi side non-squared, which is equal to the sandwiching of the psi on mi degree mi. Okay, and so one thing we can do to make our notation a little easier is noticing that when we want to calculate this probability, we don't need to, how do I say? I guess the simplified notation a little bit is we can not know this. We don't need to know the full detail of mi. We don't need to know this ei that equal to mi degree mi. Okay. So because you see the probability here, so probability I only depend on this mi degree mi. Okay. So instead of writing state of operator mi, we can write the state of operator ei. Okay. And yeah, and from those ei, then we can calculate the outcome probability. Okay, and so we are losing a little bit of information on mi. That is, we are no longer know the post measurement outcome state. That's mi side, but from those ei, we can know the measurement probability. Okay, but sometimes we only care about the measurement probability, and it's a little easier to write ei instead of mi because, well. First, you just see the notation a little easier. Okay, so the notation here, so you see the pi instead of sandwich is mi degree mi, you are just sandwiching ei, And also the completeness relationship is easier than this mi, because then you just have the sum of ei equal to identity matrix. Okay, and also all those ei will be positive. Okay, and yeah, so we should have some notation here. So those ei are called PO. So those ei is called POVN. Okay. Okay. So ei are called POVN. And it can be proved that every measurement has a POVN, and every POVN corresponds to some measurement. Okay, so this POVN standing for positive operator value measure. It's just a really generalized measurement, but with a bit of lazier notation. That is, you have those positive EIs that are summing to 1, and positive EI, they sum to identity matrix, and they will tell you the measurement outcome, but don't tell you the post-measurement state. Okay, and then here we show a little bit of using POVN to write down, to say something that's a little easier. Okay, so suppose we want to go back to our state distinguishment problem. So we want to distinguish 0 and a plus. Okay, and so we use a POVN that has those 3 elements. Okay, so E1 equal to projector on 1 scale to something, and E2 equal to projector on minus scale to something, and E3 equal to identity minus E1 and E2, and okay, and so we want to check this is a POVN. So easy thing to check is the summation of all of them to identity. That's easy because by construction E3 plus E1 plus E2 equal to identity. And the hard part to check is that they are all positive. And that's exactly why we have this funny coefficient on E1 and E2 here. That's because with those two coefficients, E3 will be positive. Like you can check it yourself. Okay. So we have these 3 outcome POVN, and we can think about what happened when you put them on your state 0 and plus. Okay. And so these three outcome POVN will be a nice thing to distinguish between 0 and the plus, because excuse me, it's a nice way to distinguish your 0 and the plus, because you see that these 1 and 0 are also going to each other. So E1 on 0 is 0. So so if your input state is 0, then you will never see the 1 outcome. Okay. And so the other way to say this is when you see the 1 outcome, it must come from the plus state. Okay. So if you see outcome 1, then you must you must have the plus state. Okay, as the input. And on the other hand, so similarly, E2 is also going to plus state. So you know that when the outcome is 2, so you know that when your outcome is 2, then the input state must be the 0 state. Okay. And yeah, but so that's good. So you see that when you see 1, then the outcome must be plus, and when you see 2, the outcome must be 0. But when you see 3, then you don't really know. It can be either come from 0 or plus. Okay, but this is something that's a little nicer than the previous way to distinguishing 0 plus. Is in that when you see 1 and 2 outcome, when you see 1 or 2, then you never make a mistake in distinguishing whether it's 0 or plus. But the catch here is that it's not a perfect distinguishment, because when you see the E3 outcome, then you don't know anything. Okay. Yeah. And I think we are just on time, and we finish the slide. So yeah. So that's it for today. And Mid-Autumn Festival, so we don't have class. So we will see you on next Thursday. Okay. So yeah. See you next Thursday.